Hello, everybody. Hope everyone's having a great morning. I'm here to talk about the hyporheic zone and the important process that happens there called hyporheic exchange, where surface water and groundwater are mixing. We'll talk about what it is, how it can change, why it's important, and what are the best practices to study it. So my research this summer studied a stream in northern Colorado called Little Beaver Creek. We used, for the first time in a field setting, a geophysical method called electric resistivity to understand the complex hydrological processes in the subsurface when logjams are present. So on the picture on the right, you can see our logjam site, where on the right we have the logjam that we studied, and the resistivity line is running across the stream to better understand the hydrological processes underneath. We'll talk more about why we care about logjams and the extent of the exchange and how that cable is used to help us understand underneath processes. So let's pretend that we're a water particle. We're floating down the stream in northern Colorado in about early June, and we are maybe floating with some friends, talking, chatting, talking about current events. And as we're floating around along the stream, we see a log jam, a series of built up wood that is blocking the stream. And we get scared. We might get separated from our friends. That buildup of wood might actually resist us staying together. So log jams increase hydraulic resistivity, hydraulic meaning water moving under pressure, and that sends the water deeper into the subsurface, which increases the time spent in the subsurface. And while we're in the subsurface, we are probably in the hyporheic zone. Hyporheic in Greek means under stream. And the full definition is that it's a region in the subsurface, under and around the subsurface where groundwater and surface water exchange. And a variety of things may change the extent of the hyporheic zone. So one of them being the flow, the rate of water, and other stream features such as log jams, pool and refill sequences, meanders, and boulders. So while you're in the subsurface, you're seeing some pretty cool things. Your friends would be so jealous. While you're in the subsurface, you're coming with the nitrogen-rich surface water, and you're seeing microbes denitrifying the water, taking that nitrogen away, which actually helps the growth of plants underneath. And while you're coming up, you are picking up some hitchhikers, dissolved oxygen, which help purify the water as well as the local ecosystem. And that logjam that you just went through wasn't there last week. Logjams tend to form very quickly due to floods and beavers, and they change the extent of they change the ecosystem fairly quickly. Engineers actually use logjams for managing and conserving ecosystem purposes. They get built across the stream to help water quality, and so you can see how the hyporheic zone as well as log jams, how much they influence the water quality and quantity of water resources, which makes their studies very important. So traditional methods of measuring the hyporheic zone are intrusive and incomplete. And by intrusive, I mean that when we are going on the field and installing these boreholes, we have to dig 1 meter deep inch holes with very heavy equipment. And by incomplete I mean that when we put sensors into these boreholes, they're only able to detect a change in voltage or resistivity at that one location, which limits our understanding. Because the hyporheic exchange zone is a spatially and temporally variable domain, higher dimensional analysis is needed. So that's where electric resistivity imaging comes in. So our setup goes like this. We put electrodes across the stream at 2 reaches. one on our logjam, as you can see on the right picture, and one on our control in our below picture. And we attach a cable to these electrodes and connect it to a resistivity meter. Then we inject salt upstream because it is conservative and also conductive. And by conservative, I mean that when the solute is washed out of the stream, it's not harmful to the ecosystem, and it's conductive because salt itself is an electrolyte, and it's easy to be detected on a graph where we can start the injection at the end of the injection. So after the resistivity meter sends a current in a certain pattern through these electrodes, it penetrates underneath. So physical data like voltage and resistivity gets sent back. This tells us about the subsurface. In this example below, you can see a cross-section of the subsurface in terms of resistance. The purple shows a high resistance and the blue shows low resistance. We can deduce that there's bedrock underneath because the solute was not able to go through that material. In order to get maps like this, we have to invert resistivity using a certain program. For our study, we used R2, and then we used MATLAB to process and plot the data. So after we get the raw data from the resistivity meter, we then have to process it. We have to calculate bulk or apparent resistivity, which takes into account the electrode spacing. K is the geometric arrangement of the electrodes, A, M, and B being the electrode position. After we calculate the apparent resistivity, we then invert it to conductivity to better see that electrochemical change in the subsurface. We also took fluid conductivity measurements, which is that inaccurate point measurement that we talked about. We placed them into the stream to measure the homogeneous surface water. And by homogeneous, I mean it's all the same material, just water. And this is in comparison to that apparent resistivity, which measures the heterogeneous subsurface, such as that includes soil, rocks, and groundwater. So what do we get out of this? We can first compare fluid and bulk conductivity. So as you can see on the graph, fluid shows minimal tailing. And by tailing, I mean it is the slow exponential decrease that we are seeing at the top arrow. And we're seeing minimal tailing in fluid, and we can compare this to our bulk conductivity that measures that heterogeneous subsurface. And the bulk resistivity is showing us something completely different. At the end of the injection, it does not go straight back to background. Some salt is still being detected by the electrodes, and it's slowly leaching out of the subsurface, and this can be seen by that shallow decreasing slope. It's also important to note that the noise that we experience from the fluid EC. This could be compared to the apparent resistivity, apparent conductivity, which shows the smoothness. We can also compare our control reach and our logjam reach. In our control, we noticed a slight bump after the tracer ends, and we did not see that in our logjam reach, which is taking a slower time to return back to background, which may be due to that hydraulic resistance it's adding. We can also compare our flow. When we got out in the field in June, we measured the rate of the water being around 0.9 cubic feet per second due to that ice melt. And we can compare this to July, which is about a fourth of that discharge. And you can see that on the graph by the red arrows showing that in July, the injection rate is slower and it returns to background at a later time. And the bulk tailing, so what does this all mean? Our bulk tailing is showing the subsurface taking in that solute and releasing it at another time. And at our logjam reach, it implies that the slower movement in the subsurface is due to the increase in hydraulic resistance. We also saw that flow rate may actually influence the rate of discharge as well, as you can see in that graph where we look at both July and the logjam, which is still not at background. So some key points that we got is that fluid EC data is incomplete, and bulk EC is the best way to look at the subsurface. We also learned that low flow in logjam may indicate longer residence time, which means more filtration. So to wrap up, my research this summer studied the connection between logjams and the hyporheic zone affected by logjams by using resistivity. We learned that logjams and low flow may increase the extent of the hyporheic exchange. It also confirmed that electroresistivity imaging is the best way to model the subsurface and the hyporheic exchange. The knowledge acquired will lead to improvement in conserving, managing, and restoring riverine ecosystems. Thank you for listening. I want to thank Aisha and Melissa for keeping our heads on during this internship, Nadine, Rolf, Emily, and Megan for help and guidance with our materials, UNAVCO employees for space in their fridge and friendly morning spaces, UNAVCO interns for their guidance and support, and finally my research mentors, Kamini, Megan, and Jackie for their support as well. Thank you. I can take any questions.
Awesome. Thanks, Teodora. Do we have any questions? Shall we?
I could be the Lou. Could we go back to that image that shows the 2D, very colorful image showing the bedrock and the resistivity?
It's gonna be a while.
Keep going. Next one.
Whoa.
Time lag.
Too much clicking.
Anyway,
this one or the other one?
The one that you created. That one.
Oh, this was not created by me, just to clear that out.
One that could be created.
Yes.
Anyway, great talk, really interesting. And as we're looking at this, and it shows that, you know, the blue zone, which is lower resistivity, and then it has kind of almost that spherical, half spherical shape. What story is that telling us? Is that showing like a rate of influx into that area? Like why would you have that little bit of red, dark red, kind of almost like a boulder shape there?
So the purple indicates the bedrock, and it is getting to be a more cool color as it decreases, as it goes out. So that means the resistivity is decreasing. It might be due to sediment that is becoming less and less resistant due to being closer to that surface water and being more porous. The circles indicate just the radiation in the surface area of that bedrock, that hard material, I would say.
Any other questions?
I have a question about this same diagram. If this is a stream cross section, where would you put the sediment water interface? Is it that light blue?
Can you explain
Am I
more?
understanding that correctly?
Can you explain more what you mean by sediment water interface?
Say well, I'm just trying to understand how to visualize this cross section.
Yeah.
And so it looks like the dark blue is liquid water.
Yeah.
And then at some point there's a sediment, so the bottom surface. Where would that bottom surface be represented in this color scheme?
It would be lower at the ground. So this is just a cross section which is dependent on the sensitivity of the electrodes. It can only penetrate so far, and so we can take account. It might not in this picture have penetrated that lower region. I'm not quite sure how to answer where exactly is that area.
Okay, thanks.
Okay, any other questions? No? All right, thanks, Theodora.
Thank you.